Welcome to part 2 of Target 7A. This part is about multiplying and dividing rational expressions. So let's start by reminding you guys that addition, subtraction, very similar. Just pay attention to if it's subtraction because it's not commutative. You need to be mindful that there are parentheses around the second numerator, so you distribute that subtraction appropriately. With division, since division is the inverse of multiplication, if you recall, if we were to divide these, we'd simply invert the second piece to turn it into a multiplication problem. Some of you recall the teachers would just say invert and then multiply. So we're just going to do the multiplication. There will be one example of division, but not necessarily in the warm-up here. So whether you have common denominators or not, the multiplication happens the same way. You can just multiply straight across. There is an advantage sometimes when you have when you do not have a common denominator, where you can factor out a piece of each, the numerator and the denominator, so that you don't have to simplify afterwards. Or another way of saying is you don't have to multiply large numbers. So we notice that 3 times 1 is 3, 5 times 15 is 75. That can be simplified, but if I factor out a 3 here, I'm left with a 1. If I factor out a 3 here, I'm left with a 5. Now if I do my multiplication, 1 times 1 is 1, 5 times 5 is 25. I get the equivalent of 3/75, but I do not have to simplify now. I've done that process up front. Okay, so that takes us to rational expressions. I know that 3x squared and x each have a factor that's x, 2 and 4 each have a factor that greatest common factor is 2. So I can rewrite this as I factor out an x, I'm left with a 3x. Factor out an x here, I'm left with a 1. Factor out a 2 from that diagonal, I'm left with a 2 there, and I'm left with a 1 here. Now I can do my multiplication. I'm left with 6x over 1, which is simply 6x. Now I think you'll find that when you factor out common factors, initially, before you find the product, then that will be easier, especially when we're working with rational expressions that can include very polynomials with multiple terms. Okay, so again, division is no different. The only difference is you would invert the second part. If it were 3x squared over 2 divided by 4 over x, that would be equivalent to 3x squared over 2 multiplied by x over 4. Looking at this problem, it looks like everything's been factored except for this piece right there. From experience, I recognize this as the difference of 2 squares. X squared is a square, 4 is a square. And I know that that is equivalent to this. The square root of both the first and last terms. One is subtraction, one is a difference. Or one's difference, one is addition. Or sum. Square root of the first term, square root of the last term. One is the difference and one is the sum of those two square roots. Now I have the denominator for this ratio in factored form. I can look for common factors and cancel those out. So I have x plus 1 times 1 over x subtract 1 times x subtract 2. You do not need to find the product of these two terms. This is satisfactory. In fact, it's preferred if you keep it in factored form. Example B is a division problem. Recall that if you invert the last part and then multiply, that is sufficient. It's equivalent. Now I've turned my division problem into a multiplication problem. I need to look for common factors that I can simplify, so I can simplify early. X plus 1, they cancel, and I get 1 for each. I can factor out a 1. I can factor out an x here. I can factor out an x from 6x times x, 6x squared. And I'm left with a 6x. This problem becomes very quickly 6x. Example C is another division problem. You won't see ratios written like this so often, but you might. And in this case, just rewrite it as the numerator, this numerator divided by this denominator. Or at the same time, you want to go ahead and invert this denominator. You can turn it into a multiplication problem. Excuse me. You can turn it into a multiplication problem. Now, again, through experience, I see difference of two squares, square, square, difference that can be factored. X plus 3 cannot be factored. Both of these trinomials can be factored, and you end up with these. Now comes the fun part. You get to cancel out anything that is common in the numerator and denominator. This is the product here in the numerator, product here in the denominator. But we can cancel out x plus 3 and x subtract 1. And that looks like it. What we end up with is an x plus 1 divided by x plus 2 times x subtract 2. That would also be the difference of two squares. But you don't have to write it this way. You can leave it in factored form.